All right, I want to show you some examples. I got three functions I want to do here. Taking derivatives using the chain rule in combination with the other rules that we've already learned. So here's my first example. I want y equals the secant of x squared divided by x. Okay. Now, I see that I have one function inside of another. I've got a secant, and it's not just a secant of x, it's a secant of x squared. Okay. Now, um, to take the derivative, I've got to decide what derivative rule to use first. And if you're ever thinking what derivative rule to use first, and the rule you say is the chain rule, then that's wrong. Chain rule is like always the last one to use. I mean, the chain rule is involved, but the chain rule is times the derivative of the inside. When I'm trying to decide what derivative rule to use, I'm plugging in a value for x to see what y is. That's going to tell me what rule to use. So if I plug in a value for x, what do I have to do? Well, I have to square it. I have to find the secant of x, and then I'd have to divide whatever the numerator turned out to be by whatever x is. The last calculation that I do in order to figure out what y is divide. This is a quotient, and so the first derivative rule that I use is the quotient rule. Right? So I'm going to use the quotient rule, which tells me I need the bottom squared. I need the bottom times the derivative of the top minus the top times the derivative of the bottom. Right? So bottom times the derivative of the top minus top times the derivative of the bottom, all divided by the bottom squared. So here we go. I didn't do any chain rule there, right? That was a quotient rule. Now, within the quotient rule, I get two other derivatives to do, and maybe one of those will be a chain rule. In fact, there it is right here. What is the derivative of the secant of x squared? Well, all right, this isn't just the secant of x, it's the secant of something else. So, first of all, how do I take the derivative of the secant of x? Or how do, let's say, the secant of u? That should be secant u tangent u. So this should be secant x squared times the tangent of x squared, right? I don't change the inside. That's the same u that it was there, secant u, tangent u. But now I have to multiply by the derivative of what's inside times the derivative of x squared. That's the chain rule. The outside function here was secant, so I took the derivative of the secant, leaving the inside alone. Then the chain rule says multiply by the derivative of the inside. Right? And then I have over here, I got a secant of x squared times 1. And now I have one last thing to do here. I've got an x, secant x squared, tangent x squared times 2x, because that's the derivative of x squared, and then a minus secant, looks like sine, secant x squared. Right? Getting some things together here. Still divided by x squared. It's tempting, cancel out this x maybe with one of those, but of course that x is not a factor at the top. Right? I've also seen people say, oh, well, look, you can factor out an x squared. Oh my goodness, watch the next video in regards to that. You cannot factor out that x squared. I can factor out a secant x squared from top and bottom though. So I've got secant, not from top and bottom, just from the top. Secant x squared, secant of x squared. And then I've got 2x squared, because the x and the 2x there, times tangent x squared, and then minus 1 all over x squared. There we go. So there's a quotient rule together with a chain rule, and I wanted to throw the secant in there too, because the secant's one where the inside function shows up twice, and I want to make sure that we see it there twice. Next example, and this is one that really gets people because they're not paying attention to a couple of things. One is that people look at this and say, Okay, what derivative rule am I going to use here? Well, if I plugged in a value for x, I'd square it, I'd multiply by 4, I'd take the tangent and cube it, and then I'd multiply? Like, no, 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 you don't. What does this mean? Literally, what does that mean? It means you're going to take 4x squared, take the tangent of that, and cube the result, right? This is something cubed. So when I take the derivative, this is going to be 3 times whatever this thing is inside. Don't mess with the inside. And square it, right? So that's just the power rule. 3 times that thing squared. Then the chain rule says times the derivative of the inside. So I need the derivative of the tangent of 4x squared dx. Well, this part's done. Now I'm just focusing on this derivative. Well, this is the tangent of something. Well, it's not just the tangent of x, it's the tangent of u. So there's going to be a chain rule here, too. This is 3 times the tangent. Actually, let's just write it this way. Let's just say 3 tan squared of 4x squared. Tangent of 4x squared. So this is the tangent of something. The derivative of the tangent of something should be the secant of that same something. Don't mess with the inside. But then multiply by the derivative of the inside. This one actually is a problem with 2 chain rules here, right? But look at, you got sort of double sets of nested parentheses here. This is the cube of the tangent of 4x squared. So every time I heard that of, there's a chain rule in there. The cube of the tangent of. So now I need the derivative of 4x squared. So I've got 3 tangent squared 4x squared secant of 4x squared times 8x. And personally, I would get these things together. So I would write this as a 24x times the tangent squared of 4x squared times the secant of 4x squared. Okay. And there you go. There is the chain rule twice on that one because I had 2 sets of nested parentheses. And this can keep going on and on and on, depending on how, how far nested you have stuff. Work from the outside in. Figure out what type of function it is, take the derivative of that type of function, and then a chain rule will pop out, or a quotient rule will pop out, or something will pop out here. Let's do one more here. Y equals the square root of the cosine of x plus 3 over x plus 7 squared. Now, here we go. How do I take the derivative? Well, first of all, I recognize this as something to the half power. So this should be 1/2 times this thing. Don't mess with the inside. To the minus a half power times the derivative of what's inside. And what's inside is this cosine of something. So I've got 1/2 cosine x plus 3 over x plus 7. That's a squared. That's supposed to be a squared. That's a squared. Please make it a squared. There we go. To the minus a half power. And now I'm looking at the derivative of the cosine of something. Well, the derivative of the cosine of something is minus the sine of that same something, right? Don't mess with the inside. This, I've already dealt with the square root, and this was the inside. Now I'm dealing with a cosine, and this fraction is the inside. So I've got the sine of that same. Why do things keep changing here? That 3 should be a 7. Squared. The whole point is don't change the inside, right? But then that wasn't just the cosine of x, that was the cosine of something else. So I need to multiply by the derivative of that something else. So times the derivative of x plus 3 over x plus 7 squared dx. Well, I have to look at that and say, well, what kind of function is that I'm taking a derivative of? Well, that's a quotient. So I've got minus 1/2 cosine of x plus 3 over x plus 7 squared. That thing to the minus 1/2 power times the sine of x plus 3 over x plus 7 squared times the derivative of this quotient. Well, this quotient, I've got an x plus 7 to the 4th power now, and then an x plus 7 squared times the derivative of the top, which is just 1, minus the top times the derivative of the bottom. Now the bottom actually has another chain rule because this is x plus 7 squared. It's not just an x squared, it's a something else squared. So this is 2 times x plus 7 to the 1 power times the derivative of what's inside, but the derivative of x plus 7 is just 1. So anyway, that's kind of big, but we can take that derivative by just working from the outside in. And for as much work as this is, it's a whole lot better than taking the limit as h goes to 0 of this thing with an x plus h plugged in minus this thing with just an x plugged in, all divided by h. Right? Work from the outside in. Deal with only one thing at a time. Eventually, you'll take the derivative of every piece. Somewhere we took the derivative of this cosine. Somewhere we took the derivative of that squared. Every piece gets its derivative taken somewhere, but you're going to start from the outside and work in. This is a square root, so deal with the square root first. It's a square root of cosine, so the cosine gets dealt with next. It's a cosine of a quotient, so the quotient gets dealt with next. And in that quotient, there's a power rule, and that power rule gets dealt with at some point too. Start from the outside and work your way in.